Mm-hmm. Mm-hmm. Cool. Okay, let's get it. Had break took longer than expected. Like 40 minutes longer because I was cooking. Eating took a long time to eat. Had some cabbage shit. Eh. Okay, doke. Let's go. I still have time. Just have to cut into a break a little bit. So I've got this till 2 something, and then another 2 more after, and then one break in there, something like that. Yeah, I'm good. So we'll be doing like 5.5 or 6 hours of studying today. Okay. A superior solution being what? Just if we call it with nothing, then. Mm-hmm. Makes sense. Yeah, because overloading would say, hey, this is the one that actually has the parameter matching the argument you're doing. This is the version we're calling, versus the version without parameters is the one that is called when we are not providing anything. Just like, let's see. Like if I call a function to set target, but I don't provide a target to set, then the function will yield an error, or well, it'll just do standard C error and say error, no target provided. That way in the game, if you're using that rocket launcher, you're in a plane and you're about to shoot, but you don't have a target locked in, then you get an error, not in the code, but in the game. Because we're calling something and not passing it what we should be, therefore the function should handle that and say, hey, by the way, this is the overload that's being called because you didn't give any parameters, buddy. Which may be good or maybe not, but regardless, the code handles it. Yeah, so we say, and we have a struct, and in one case, we have a reference to a struct, because this is a type, so a struct, reference to a struct, and then in the other, we're not passing anything. If we pass nothing, nothing. We call print ID with no ID, well, your ID is not known, buddy. But if we call it and we say, hey, here's a reference to an employee that exists, we're doing a reference because it's expensive, probably, to pass this. So, look at it.
And get the ID.
That ID, boom. Versus a pointer. Ah, gotcha. So if this is a pointer, so if this is an actual reference to it, we can do dot ID. But if it's a pointer to a struct, then we do point to the ID part. Okay, interesting. Something like that. Not exactly sure how that works, but I'm not at the struct yet, so I'm not sure. Okay. Any quiz action? No, not yet. All right. Next. Makes sense. Yeah. So if we assume that, oh, gotcha. Because if we copy the employee, we're copying a standard string. Even if the employee is cheap, standard string is not. And if we say that that a compound type is a type that's defined in terms of fundamental types, well, I guess I don't know if we include. I don't think we include standard string as a fundamental type because it's just in a library that we happen to maybe use. So I'll say it's defined in terms of fundamental types and or well, but if we have a class, if we have a struct and it's made of 2 other types, a struct is a compound type. I'm assuming always. So I'm gonna say made of other data types. Like if I had a class and it's made of multiple structs, then I guess it's a compound, right? So this employee specifically is expensive because it's made up of a standard string, which is expensive to copy. So instead of copying it here, we're just going to look at it in memory wherever it is. In this case, here it is. We have an instance of a struct. We're going to pass it, a reference to it, but we're passing it as a reference, passing it as a reference, received as a reference. I'm just not saying the received part. That way I can still say passed as reference. I don't like saying passed by reference because I'm not passing it. I'm not passing a reference to it. I'm passing, well, yeah, I'm passing it. It's just receiving it by a reference, and boom, it's getting the ID. Cool. And then we're doing the same thing. where instead of actually passing a whole struct, I can pass in Dave62, even though this is a C-style string, not a standard string. Does that mean this yields a temporary struct? I guess so, huh? Because I'm passing an initializer, and if the initializer matches the properties of an existing struct, I suppose it's getting a temporary one, huh? Okay, so we could say, hey, if there was a guy named Dave and he would be 62, what would his ID be? Oh, 62. Okay. Prefer standard optional for optional return types. Yeah, as long as we don't have to. Well, yeah, let's see. For optional return types, where we need to say, hey, did this thing succeed? Is it optional? Optional meaning, optionally, we return the expected value, a quotient when we're doing division in a function. Alternatively, we don't return the value. We return the optional. And in that case, it is optionally not initialized with a value, or rather, it's initialized with null option. Null opt. I prefer function overloading because it's probably easier, so we just call the right function instead of calling it and then checking if it's null and then going. Prefer it when possible. What is a case where function overload wouldn't be possible? I'm not sure. I'm trying to think of a case where we do an optional that's default initialized to null opt, but in comparing it to function overloads, where we just say we have one, instead of saying null opt and then having that function check if it's null opt and do this, and if it's not null opt do that, we could have a function that if there's a value to this, and another overload where if it doesn't have a value do that. What is a case though where we couldn't do the overload part? I guess when there's a function and we have to have the same function handle the behavior, like I want to, well, where it needs to see, I don't know, there's something else in there maybe that's expensive. There's just some case where we need to call one function for some reason. Maybe there's something that can only do one instruction, or maybe there's something that's, not sure fully. I'll come to that at some point. Otherwise, use it when we're passing by value, because if we're passing by value and it's an expensive thing, no go. Do that via reference or do that via the pointer. Well, in that case, we can't do it via reference because there's no optionality. You simply have to pass it a reference to something that's valid. There's no reference to null pointer or to some null object. So pass it a pointer to something to evaluate whether it's true or not, or optional, depending on whether we have to pass by value or not. Gotcha. Thus, favor the pointer version when things are expensive to copy. Gotcha. KO. Like, for example, excuse me. Okay, or let's say, what would we do? Okay. And we could just do the same thing basically. Okay. And then we could say, so there's a mission Hector, then there's a, do we want it const? I guess we could. Const, standard, optional, standard string, current mission, and initialize it with a we can make a const expression just to try. Standard optional returning a standard string. Check mission, and it takes we could use it as a parameter. We could say standard optional taking a standard string. Mission, and it's initialized with, and it's standard null opt. How about null opt? Yeah, standard null opt. And if mission return, well, let's see. Return mission, else return. Well, this would be converting to standard string. Might not be super a big issue, but no valid mission. Oops. Cool. Okay, and we'll initialize this guy with check mission, and it will pass it mission. Cool. It's valid because it's initialized with something, so it's not null opt. And then, yeah. The problem, though, is that we are actually copying the value of this guy here. So instead, it's probably better to just do, oops, well, I was trying to select it on and replace it with a parenthesis, but I can't. In this case, we're just going to do a const standard, so we can't fuck with it. And I could have done a const standard optional too, but a const standard string pointer to a const standard string, and is initialized with null pointer by default. And in this case, if it's valid, then we can return the dereferenced value. And then in this case, we can, yeah, we could just pass the address of mission. In this case, it's actually returning the standard string. It's returning a standard optional, which can be expensive, but we're at least passing the reference. But then we have this return value here, which is copying a standard string back. Well, we've passed it in, so we could just return it back. Honestly, this could just be a const. This could just be a pointer to it, huh? Yeah, I mean, and then in this case, does this even, I mean, we could just leave it a standard optional, I think. Because optional cannot be, what does it say here? Okay, so if we're returning standard string pointer, uh-oh, doesn't like that, huh? Oh, well, what if we just say this? Yeah, there's none. Oh wait, yeah, because this needs to be a standard string pointer. That's returning it from a const, so we could make both of these const. Okay. Oh, and then we could just say else return. I can't have a pointer to an R value. Let's just say test. Nothing. And it doesn't work. What does it say? Yeah, because you can't convert this guy to a pointer. I mean, this is a pointer to a const char. Or at least, I guess it's just an array of const characters. To that, instead, we'd have to create... I mean, I could create a static and do some other stuff. Or we could just... Oh yeah, well in this case if it's an optional, then we just return null opt. Okay, bunch of different ways of doing this. Yeah, there it is. Or the compound. Yep. Okay. So so does that mean that a standard string is a compound type? Which means that at some point it's composed of fundamental values. Compound data types are data types that can be constructed. Let's look through this, see what we've got. Got some stuff, some more stuff. Nice. Cool. Alright. Compound data types are constructed from fundamental data types. Composite data type, okay. It's a longer name, it's annoying. Be constructed from fundamental data types, cool. Why not R, that are constructed? Well, I guess maybe it could be for declared with nothing in it? I don't know. I mean, but then again, that would be like type defing something without saying what it's using. Maybe not. Maybe it's not possible. The value category. The value category? I remember that term. I mean, the type of value that it... type of thing that it returned, that it... Oh, okay, so maybe like the value category for a pointer or a reference is an object, whereas the value category of the object itself is a value, whereas the value category of a function might be an object or a value. And maybe if we even have such a thing as a function pointer, which apparently we do, the value category of that pointer would be a function, something like that. It seems like it's the data type of the... seems like it's the low-level data type, the data type of the thing that's being returned. For a function, it's just a value. For a pointer, it's an object, because we're looking at an object through the pointer. If it's a pointer to a pointer, it's also an object, because we're looking at a pointer, which is an L value itself. An L value is an expression that evaluates to a function or an object that has an identity. And thus, an L value is a is something, it evaluates to something with a memory address. Oh, or an identifiable memory address or identifier. There are modifiables and non-modifiables. Yep. R values are non-L values. Literals, except a string literal, because those, I guess, are pointers. The return values of function, because they can be incremented, and the return values of functions are operated. Gotcha. Because these are little temporaries. Yeah. Yeah, because if I call a function get thing, and I look at the get thing in parentheses, that yields a return type, return value, but it doesn't exist anywhere. It's just, or it's not stored anywhere that has a memory address. I can't look anywhere to see it. It's just temporary. Once a reference has been defined, it's applied to the object being referenced. Yeah, it's like a snapshot of it where you can actually change the object through the snapshot, through the picture. Types L value and R value. Yeah, because there's L value reference, but then there's L value reference to const, which is an R value. L value reference. Hold on. An L value reference is the alias. This is an alias for an existing L value. Man, I've just been calling these the same things. L value references are L value reference variables. Yeah, I don't know if you can have a temporary L value. I don't think you can. There's no such thing as like a temporary L value reference. So why is there the term L value reference and L value reference variable? Seems like they're synonymous. I think Zyrtek's working. Allergies are getting better. Okay. It's bound to it. Yep, sure. Or function. Interesting. So does that mean, do I just pass in E as a call? Or is it just the identifier? Like I could have a reference to a Mersenne twister and pass the reference into a uniform int distribution and it would call it. But in that case, it's not really a function. It's an object that has a member function that's called with operator or parentheses with no parameters, I guess. Yeah. The referent. Yep. Can't be bound to non-modifiable or R unless they're const L value references. Yep. Which we see later. L value reference to const. Yep. Yep. L value references to non-const or a non-const reference. Cool. Yep, can't be reseated. It's only bound to one thing, and it must be initialized with the thing as its bindee, as its referent. Yep, we got a dangling reference. Yeah, because like if we have a function that creates integer x that has the value of 5, and then I return, and then I return 5, or I return x, but the return type is a integer reference. Oh fuck! Excuse me. The caller would use that return value, which would be a reference to x. But now that x doesn't exist because the function is already terminated, has been evaluated, it's gone. Well, x has been destroyed, which means we have a dangling reference which yields undefined behavior because we don't know what's there anymore. Maybe the value is the same, probably is, maybe not. Assume it's not. Just like if you had default initialized a variable by not initializing it, leaving it uninitialized and used it. Well, undefined behavior, bucko. Bucko. Const to make sure that, hey, this is a reference to a const object. We cannot modify it through this reference. Yep. Even though the object might not be const. Such a reference is an L value reference to const or just a const reference. Sure. Or reference to const. Yep. Modifiable, non-modifiable, and R value. Yep. Temporary object is, it seems like it's an R value, basically. Also sometimes called an unnamed object or anonymous object, okay. Excuse me. Created for temporary use and destroyed within a single expression. Yep. After it's a value, excuse me. After the expression is done, it's gone. When using pass by reference, we have a function parameter that takes a reference and we pass it an object or we pass it a reference. Regardless, it's creating a temporary variable. It's getting the address of that thing because this is a reference. It's just a pointer. A pointer is just passing value, but it's passing an address as value, which we can access to go and look somewhere in memory instead of making a copy of that value. We can just look at it. Yep, parameter is a reference instead of a normal variable. Yep, normally const, so we don't fuck with it too. So it cannot be changed within the function. Yep, the reference parameter is bound to the appropriate argument. Yeah. So third parameter is a constant reference. Oh, our third argument is an int. Well, guess what? We get a reference to it, whether it's an R value, a non-modifiable L value, or a modifiable L value. Yep. It's an alias, so we are not copying. We're just looking where it is. Technically, there is a new variable or a new object that's holding that address that we're looking at, and it's automatically dereferenced, but it's cheap. because we're only passing a little integer action, a little address action. The address of returns the address. Yeah, really it returns a pointer to the object, the unary operand. Yep. And that returns the value at the address. As an L value. Yep. Which is why we can't have a pointer to a reference, because the reference could be to an L value or to an R value, and boom. Let me fully check that. Okay. No pointers to references. I swear, man. But whatever. Okay. Pointers hold memory addresses. Yep. 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 Wild pointers are those that weren't initialized, just like it has a garbage address instead of a garbage value. But technically, that would, well, yeah. Dangling pointers. Dangling pointer is one that pointed to a valid object, but now no longer does, because the valid object was destroyed. And now we don't know. It's pointing to the same spot, but we don't know what's there anymore. There are no longer walls that prevent other values from coming into that variable and fucking it up. Now we're still looking there, but the walls are gone. We don't know what's there. It's like going back to Skalitz in Kingdom Come Deliverance. The walls are gone, buddy. We don't know what's there. Probably bandits, robberers, rapers, the whole thing. Okay. A null value is something else that a pointer can hold, because really, I guess a null pointer is a pointer to null. That means something has no value. And when it's a pointer that holds it rather, the pointer is not pointing to anything. A null pointer. Ensure 0 or all caps null are converted to that null value or used as in the context of a pointer. But it fucks with overloads. That's the main point. If we have an overload of something that takes an int versus an overload of something that takes a pointer, and I pass in null pointer, it calls the pointer one. If I pass in 0, it should call the int one, but maybe I'm using it in a context with a pointer, and I want it to call the pointer one. Well, can't, buddy. So use null pointer. Yep, that way we can test a pointer to see if it is null or not, because it shouldn't be dangling, because it should either be null or not. Yep. A pointer to const. It's a pointer to an L value that is non-modifiable. Cannot modify it through the pointer. Versus a const pointer is a pointer to who the fuck knows what. It's an L value. Well, it could be dangling. It could be, I mean, it's to an L value or it's null really. It's just it might be to an invalid L value or a dangling one. But we can't reseat the pointer because it's const. It's unchangeable. Yep, points to a constant value, sure. But really it's to a const L value. A const pointer is a pointer whose address cannot be changed after initialization. Yep, we initialize it, or well, yeah, we initialize it with an address. Oh, well, it's stuck it's stuck wild. Or it's stuck null, or it is stuck with a certain object. Yeah, and whose is correct here. So we're treating it like it's a person, like the pointer owns something, so whose is cool. Okay. Instead of saying the address of which, I would rather just say whose address. A const pointer to const is a pointer that cannot be given another address after initialization, and it's initialized to point to a non-modifiable L value. Yep. Passing by address, yeah. When passing by address, we're creating a temporary that holds the address of the object that we are passing as an address. That value is copied to the parameter, and it could be copied back from the return value. Let's do 30 push-ups real quick. This will be tough. Okay. 1, 2, 6. Wasn't too bad, but I couldn't talk after like 22. Okay. Feels better. Yep. Yeah, we provide the address of something. Yep. Address is copied into a parameter. Whitehead. Yep. We can then dereference it to change it, sure. To read it, to change it if it's non-const. Yep. Return by reference. Yep, better make him static, buddy. Or make him be the reference to a reference parameter or to an existing object. Yep. And really what we're doing is we're creating a temporary that holds the value, the address of the object, bound to, it's just holding an address to it. And we are initializing something to take that value. So really it's object, object, want, object, B, to have the value of A. Cheap, no copy. Instead, copy where this guy is in memory to this temporary, copy that to the return to the final value. Or rather, initialize a temporary with the memory address, copy the value to the object that is going to become a reference. Or well, is a reference, but will be initialized. Or will be assigned the value at the reference, either way. Well, we could make it a reference to the object that we're talking about, that we have an address of, or we could just have it be a variable getting the value of that object cheaply. As cheap as possible without extra copying. There's the cost of assigning the variable, but then there's the cost of copying it to a temporary too. Turn the reference that is bound to the object. Why is this wet? Getting better at looking through the bottom underneath my glasses to see the world. Reference to the object being returned, sure. Yep. There's the cost of bringing it, or of initializing something with it, or assigning something it, but there's no extra cost of the copy. Because we copy it into a temporary, and then this variable doesn't exist anymore, and we copy the value from the temporary, but we get a temporary. Instead of just saying, hey, copy the address to a temporary. This is the expensive part. The address is cheap, but the actual value of the object, the value of the reference, the value of the referent is the expensive part. Yep. And the reason it's dangling is because we have an object that exists somewhere in memory with a value. We are returning a temporary variable that will exist after the function is concluded, but only for its one expression. And it is taking the address of this object. So we have to get it from this object to the function we're returning to. So create a temporary variable. It gets the address, copies it, but it's cheap because it's basically an integer. It's a hex number. And then we are basically copying the address to make a reference, or we're looking at where that address is. So there's no value that's being copied except the address itself. The address of the object, not the object's value, is being copied. Yep, otherwise we get some dangling action. Yep. Yep. Yeah, because if we have an object that's not static, not global, or known elsewhere outside of, and not being passed in as a parameter, it's local and it's going to die. We copy the address. Cool. We didn't have to copy the expensive standard string's value itself. We just copied its address where it is in memory. In this case, it's local, so it's not going to be there forever. Copied it, passed it in somewhere. But we're copying the address of something that has already been destroyed. We've created the temporary with the address. The object is then destroyed. The function's done. And now we're using that address. Ooh, that's like using a variable that has been uninitialized. We don't know what value is there. So instead, we make it static so that the object is alive, so that we copy its address, the function ends, but the object persists. And then we can copy that address and look at it, and the object still exists. It's global, or it's static, or it exists in the current function by passing it as a parameter or as a reference. Yep, because if it was passed in, it exists in the caller's scope. Therefore, it will still exist after the function's done, after the function returns. If a function returns a reference, and it's used to initialize or assign a non-reference, yeah, because reference is dropped. Just like the top level const will be dropped too. Type deduction drops references and top level const qualifiers. Yep, we can reapply. Yep, sure. Return by address is similar, except we're doing a pointer. And type deduction behaves in some interesting ways there too, depending on the syntax. If we're just using auto, then it's a pointer, but it will drop the const of the pointer. We could reapply that. We could do auto pointer, and then it'll drop the const of the pointer. And either we can explicitly put const before to show, hey, by the way, this is a pointer to a const, or we can leave it as is, it's still a pointer to a const, and put it after to make it a const pointer, or leave both. R value, temporary. For each expression, indicate whether it's an L value or an R value. An L value evaluates to an identifiable object that exists somewhere in memory with an address. In this case, we have an R value because we don't know what 5 is. It doesn't have an identifier, it doesn't have an address. It's just an unnamed object. It is a temporary object. R value, yo. In this case, integer x is an L value. It's identifiable by x. So when we evaluate x, it evaluates to this object that exists wherever it does, L value. X plus 1. This is an R value. Why? Because x plus 1 is not identifiable by anything. We have taken the literal, well, we've evaluated x, but then added something to it. We get an R value. Yep. Return value is a temporary variable. We can pretend like those are two parameters to a function that returns the sum. Well, that sum isn't stored anywhere. It's not called y and we can look at it. It's temporary. Therefore, R value. And foo returns 5. It returns an integer that's 5, but it's not stored or known anywhere. It's an R value. Because this is a temporary. Max xy. This is a reference to something that's passed, okay? So we return max. In this case, it's probably going to return, yeah, it returns y. In this case, we're talking about hold to the right, the max. Well, the return value is a reference. It's not a temporary, it evaluates to the variable. It's an L value, yeah. And it's not returning a temporary value that's not stored anywhere. In this case, it's returning y because x is not greater, so it returns y. We get this ternary right here. True, return this. False, return this. Okay. Thus returns y because y is greater than 5, or y is greater than x because 6 is greater than 5. In this case, it's returning this guy. It's returning y via reference. We're looking at y. Y exists. Y describes the value that we're doing. We evaluate it, it evaluates to y. We look at a reference and evaluate it, it evaluates to y. Thus, L value. The output of this program, x and y, 4 and 6. We have a reference now, an integer reference that's modifiable to x. We increment it, so now x is 5. Reference can't, well, hold it. We can't reseat, but we can assign the value. So now we're assigning the value of 6 to this, and now we have x is 6, y is 6. And now we're incrementing this, so we get 7, 6. Boom. Yep. Because really this shit doesn't matter here. We're saying, hey, we have a reference to x. Oh, well that reference, which is an alias for x is now getting this value. X is now getting 6. 6, 6. Reference is still x. Increment x, 6 plus 6 is 7. 7, 6. Because this guy's always been 6. Cool. Yep, reference is an alias for x. X is now 5. Oh, x is now 6. X is now 7. Boom. 2 reasons why we prefer to pass arguments by const reference instead of non-const reference. Instead of non-const. So it's the const part. Well, 1 could be so we can pass R values. Which is a temporary that exists in the caller. The R value prolongs its lifetime until the reference prolongs its lifetime until the reference is destroyed, which is at the end of the function. Something like that. We can and that works, right? Reference to a const int. No, not Dark and Darker, bro. Or Darkest Dungeon. So one is so we can pass in literals. We can pass in our values. I could pass in a call there. I can't modify a temporary. So if I passed in a call as an argument, it's not going to work. It's a temporary. So one, we could do that. Two, so we don't change it. So if we pass things by const reference, everything can use the value cheaply, just like it could if it was non-const reference, but we can't change it. So it's probably for safety, so we don't change the value. Two, so we can also expand how many values we can pass, which is including our values now. What else? Const reference versus non-const reference. The difference is const reference can now include our values, and it prevents us from updating. I think those are the two reasons, really. I think, is there a third? Let me rack my brain. That's all I can think of right now. We can pass additional values, meaning our values, and we can't modify the value, which means that it's safe. References already can't change. We can't assign anything to it, so we're protecting it. I think that's all I can think of. I think those are the only two. A non-const reference can be used to modify it. But if we don't need it, we may as well do it so that we don't change it. Exactly. That's one. And the second is that non-const references can only accept modifiable L values. Oh, true. It's not just that const L value references can also accept R values. They can also accept non-modifiable L values, because a non-const reference can only accept modifiable L values. Whoops, I missed half the piece there. Modifiable L value and non-modifiable L value and R value. Yep. Or really. That's easy. The difference between a const pointer and a pointer to const is that a const pointer cannot be reassigned to hold the memory address of another object. A pointer to const cannot be used to change the value of the object whose memory address it holds. A const pointer is a pointer whose address... I'm going to try and speak in idiomatic, literal, spoken English, just to see how it sounds, huh? A const pointer is a pointer whose address cannot be changed. Cannot be changed. Cannot be changed. It cannot be repointed at some other object. However, the value of the object can be... of the object being pointed to can be changed, because the pointer is const, the value it is pointing at is not, because otherwise this would be a const pointer to const. A pointer to const, or a pointer to const, is a pointer that is pointing at an object whose value can't be changed through the pointer. However, the pointer can be repointed at another object. Write a function named sort2. Wait, I've already done this. Okay. Write a function named sort2, which allows the caller to pass two int variables as arguments. When the function returns, the first argument should hold the lesser of the two values, and the second should hold the greater of the two values. Int, we could do that. The standard swap in the algorithm header can be used to swap the values. The following code should run and do stuff. Okay. Cool. I've already made that. I will do it though. As you wish. Whoa, whoa, whoa. Chill, buddy. All right, you ready? Okay. So we have int x is 5, int y is 7, fn 5, 7. Fabrique Nationale, just like the scar. We need standard character output. Oops. What does it want? Oh, okay. Wait, same thing? Just do it twice? Okay. I could do... Well, the point here is this is a void function. So we know that this... And maybe it can happen at compile time, but no, because these are not const expressions, so it doesn't make sense to make the function const expression. I'll still do it though, just in case. Const expression void sort 2, and we could just pass via reference. We could also do a pointer. Either way, reference is safer though. Okay, this will take an int reference. Sure, x, int reference y. And then we can say if x is greater than, well, if x is greater than y, well, I guess I'll include it. Include algorithm need standard swap. Okay, then we can standard swap x, y. But then I could do another that's const expression void sort 2 and my sort 2 int x or int reference y. If x is greater than y, then int z is initialized to get sure. I think that makes the most sense. And now x is y, y is, oops, sorry. Let's do x. X is now y, and y is now z. Temporarily store x's value. Swap x to get y's value. Y gets x's value via temporary z. Cool. And we could say pre sort 2. X, oops. X What the fuck is happening? Oops. Pre-sort 2 and the line X, X, Y, Y. Oh, so I guess this should be 7 and 5, huh? Yep. At first, pre-sort, it's X and Y, and then I could say post sort 2. Pre-sort 2 is 7 and 5, now it's 5 and 7, cool. And sure, I could include this header just to do that, or I could just do a little temporary my way, and I could just, alright, boom, Control X to remove the whole line, remove those, and I could just do my sort 2. Ooh, let's make this fun. How does that work? I do an inline namespace. Hold. Versioning, I think, is so an unnamed namespace is to make everything inside of it have internal linkage in bulk instead of making all the functions static and all the variables const expressions or other stuff. Because otherwise, yeah, I have to make it a const. If it's a global, if it's a non-const variable, I have to make it const or const expression, right? Or put it in an unnamed namespace. Okay. Or in a static function as a local variable, because then the function can't be accessed, nor can the variable. But then again, the variable could only be accessed from within inside the function, so it doesn't matter. So, if I put 1, I think the point is that I can put 1 in an unnamed namespace, and then 1 in an inline namespace to do some swip swap. Oh! So if I put it within a namespace, it's only accessible within its own namespace. So I could still access. Let's just make this called sort 3. What if I do this? Fuck. Okay. I guess it only works if it's actually in its own namespace. So I could do this, and then I could put this, oops, in an inline namespace. They're both sort 2. And so I could say swap sort using algorithm. Excuse me. Wait. Oh, because it's outputting now. So because we're using standard character output, we cannot use const expression because standard character output only executes at runtime. OGG. So this is the inline algorithm, or sorry, this is the algorithm one. But all I have to do is remove inline from here and put inline here and bop. Uh-oh. Hold. Oh, this should not be. There we go. Uh-oh. Hold. So I can make that one inline, and that's okay. If I make them both inline. Oh! Wait, no, never mind. This namespace ends. I thought that it was encompassing this one for a sec. Oh. Let's start from scratch. This needs to be called sort like that. Excuse me, already has a body. Excuse me, sorry. And if we put this guy within namespace, it's ambiguous because it's still accessible. Forgot that I changed their identifiers for a sec. A non-inline O, and the point is because it can't distinguish between those two. So what was the strategy here? Wasn't it? Do I just have to give it a namespace? So this is algorithm. And couldn't this still just be namespace? So either way, this is inline. And now we're using my temporary. And it works. 7557 still 57. Or I could make this namespace mine, and then this is just inline namespace, which means it's usable elsewhere, or an unnamed namespace, so it's still usable but just only here. Okay. Specifically, sort 2. Yep. Oh, so what's another way of doing it? Let's do this another way. So we could do a pointer. So I could pass these as addresses. And then this could be receiving them. But then we need to short circuit this, test two things. This and this. If X is valid and Y. So if X is valid and Y is valid and dereferenced X is greater than dereferenced Y, then swap the dereferenced values. We still get an issue up here? We don't. Okay. And here, we need to check another thing. We'll check. Oops. We need to make sure that, hey, is X valid and Y, is X valid and Y valid? If X is false, the whole thing stops. If X and Y, if X is true, if X isn't null, but Y is null, this whole thing stops. It doesn't need to evaluate the rest. And, so this is how it needs to be. X, check if null, then compare values. Then we can switch these guys over to references. Hold. And Z is not a pointer. Z is simply an int. So we can swap the dereferenced values using the algorithm, or what's the easiest way of doing this? Control backspace, inline, top, control, delete. Uh-oh. Hold. Oh, namespace. Oh, okay. So we need to do control delete and end algorithm. And now using mine. Works either way. We can't have these guys be const. We could make these const pointers so that they can't point to anything else in their, but just that their values can change. Same thing. Control backspace. Oops. That's an unnamed namespace now. Control, oh, and actually that needs to be named something. Algorithm. Control, or no, just home, control delete, inline. That way it could be used anywhere else so that any other function that's using sort2 is now using this version. And now we're using my version. Okay, what else would we do? Anything? We could do the pointer way. That's less safe because one, we have to fucking check all this shit. We gotta check the pointers to make sure they're valid now. In addition to already checking the values and the extra dereferencing syntax. And now we have to make them const. Okay. Alright. Anything else? They can't be non-const. They can't be const expression. Well, they could be if we're not outputting this guy. So if we just delete via control X, this can now be const expression. So can this. But that only works, I think, if these guys are static. Because then they are known at compile time, and thus this guy, I think, needs to too. But this doesn't work because this isn't a constant because it's a parameter. So we would need to pass it as a pointer as a non-type template argument, it seems like. So, same thing. Okay. What do you think? Anything else? When the function returns, the first holds the lesser, the second holds the greater. Swap them. Should print 7.5 and then 5.7 and then still 5.7. So in this case, you're doing void sort2. Okay, it is. It's just what I thought. Yep, we do references. We check if lesser is greater than greater. And I guess, sure, yeah, my value should have been more idiomatic. So that it's lesser and greater instead of doing, hey, if lesser is greater than greater. Oh, well, that makes sense that it shouldn't be. Instead of, oh, if x is less than y. What's going on here? Because x and y. Swap lesser and greater. Okay, I'll redo it and I'll do better names this time. Oops. We need, and it's void, so we don't need anything optional. IOStream, why? Because we need to use need standard character output. And x is 5, and y, oops, sure, and y is 3. Pre-sort. Oops, and then x, y, and then sort2, x, y, post sort, x, y, and sort2 again. Well, we can just copy these. Oops, copy, not that. Okay, so we got pre-sort. Oh, well, I may as well just copy the whole thing. Why isn't it doing that? What is happening here? Cool. But that's an unidentified guy. He's not identified yet. Cool. Got this. Cool. Sort. Try to sort, but do nothing since sorted. Cool. Alright, we'll do void. We could do const expression void sort 2. And we could say lesser, or a reference to an integer called lesser. A reference to an integer called greater. And then we say if lesser is greater than greater, we need include, to do this in one line algorithm, we need standard swap int in this case. For some reason I don't like that. Okay, felt like severance where you're sorting numbers and it just doesn't feel right. And in this case we don't need to nest it. We can just say standard swap lesser greater. If unsorted, sort swap. Cool. 5 and 3, and then 3 and 5, 3 and 5. Cool. But then we could make this guy into a namespace algorithm, and my names were wrong too. It should have been algorithm, or it should have been caps. Namespace, inline namespace, and then const expression void sort 2 int reference lesser int reference greater, and then if lesser is greater than greater, then int z gets greater's value, lesser, hold. I think you could do it either way, and then we could say yeah, and then greater gets lesser's value, and then lesser gets z. The point here is that we have lesser and greater. Lesser is too big, greater is too small. So we get z, which holds greater, or z, which holds greater's value. Greater will get lesser's value, and then lesser will get greater. Cool. Temporarily store greater's value. Greater gets bigger value. Lesser gets smaller value. Temporarily stored by z. And now we'll have this not be const expression because this is character output, which is not done at compile time. Using my sort, and then standard character output using algorithm standard swap. Now we're using my sort. It works. Wait, how do I close this window? I can press anything except escape. Good. Oh, but sometimes escape works? Okay, I'll just press another key. I don't like that though because I still have to click into here. If I do this and I do that, that works. Yeah, I like escape better because if I run the program, press F, and I type, nothing happens. If I press F5 and I press escape, oh, actually, F escape will bring me back. Okay, so same thing. If I press escape once, still same result. So I have to press escape again to bring me back. Cool, noted. Trying to do the keyboard as much as possible. What else? We removed const expression, so it can do this. And then now we can make this the inline namespace. Not unnamed because then it would have internal linkage and wouldn't be usable in any other file that needs it. And then namespace my sort. Oops, my sort needs to be caps because it's a namespace. Boom. And now it's using algorithm. Cool. Okay. Made it exactly to spec. Coolio. Yep. And swap. That's it. Yeah, cool. Yeah. I don't think that adding one line to remove one line is helpful. I mean, granted, you're technically adding 3 lines because you have to add in a 4 lines. You have to add in you have to include the header file. You have to initialize the temp. Well, hold on. Actually, no. In this case, you have to include a header file, and that lets you remove 2 empty block parentheses. And so what? You add in the algorithm, but you don't have to create. Yeah, so it's for a couple lines less. Yeah. We don't have 2 empty braces here for the block. So it's 2 less. And we don't have to have a temporary variable. And we don't have to assign value with the temporary variable to the other. We can just do the swap in one line. So it's 4 lines less, but plus 1. So 3 lines less, all just to include a header file. I mean, I guess if the code's unused, it'll be taken out by the compiler. I don't know. I'd rather figure out how to write stuff better, but cool. Excuse me. Okay. C++. How long have we been? Hour and 17? Go to the bathroom again real quick. I gotta pee and I gotta do everything, man. I don't know what's happening. KO. Fundamental types. User defined types. Let me see it. Ooh. Struct action. Let's go. All right. The core C++ language. The predefined shit, no including, no nothing. Hmm. Oh, could I adopt some nasty syntax? Oh no. Oh wait, no, but it would need to be 5 and then that. Oh. Oh god. That's disgusting. I was thinking about that because I was wondering for a quarter of a second, why is he able to do that or that? What in the fuck? Oh, well, duh. It's just because we're just doing that. Wait, what? Hello? Hold. Oh, and then that's the for declaration part. But the point is, yeah. Well, I mean, wouldn't you just do that? What the fuck? I don't know what the point of, like, if we do that, okay, we're cool. If we do that, still, yeah, I don't know what the point of doing that would be. Because we're adding a body, but then we're putting a semicolon at the end. For what reason? Why? It's still, well, let's see. Versus, same thing, and no result. Mm-hmm. Mm-hmm. Okay. We do not need to provide or import any definitions. But if we have a new one, type alias. Yeah. Before we use it, must be defined, just like we have to include a header file for int16 in int16 underscore t. Yeah. Just like we have to have a using statement for using long boy equals double. Type alias, yeah. Yeah, I'd say it's undefined. Yep. Wow, that's cool. Ask if I give a fuck, I tell you it's undefined. Give me another look like that and I'll give you something to find. Alright, Jesus Christ. Alright, let's go. Father would know, yep, it's undefined. Definition doesn't create an object, just tells it that a length is a something. Otherwise, it doesn't know that a length is a something. Oh, to store a the challenge of storing a fraction? Or what are you talking about? Oh, gotcha. But now we could have a fraction and have it be made of two integers and then say the fraction's name dot enum or dot num or num or dot den. Numerator, denominator. I guess numer versus denom is probably better. Yeah, they're linked together, but they're not. Instead of saying, hey, I'm going to change this piece of the fraction, it's just I'm going to change y, and y happens to be the denominator in this case. Makes sense. True. Make it so you can create yourself, buddy. It's Minecraft. I'm not going to go and make a fucking world for you, but you can make it. You can make your own plugins using these tools. I'm not going to make a dang RPG one for you, but you can make one for an RPG. A whole role-playing game or a literal rocket launcher. Thanks, C++. Thanks, Bjarne Strawstrup. User-defined type versus program-defined types. Because we don't necessarily know if it's defined by the user in this case. Two different... Oh! That fucking got me! Oh! Alright, so if I take break 30, 18 minutes, then I can go to 4, have a 30-minute break, then do it. I'd rather have a shorter test then, so I'm going to take a 30-minute break now and an 18-minute break. We're going to do until 42. Oh. 30-minute break now, 18-minute break later between the tests. Because I've already cooked my food too, so I can just chill out for a minute and then leave after I do the self-test. So, cool. Alright, on to define types later. This will be cool. What are, C++ has two diff, cool. Alright, that's it. Okie doke.